So, hi everyone. Now moving to the second part of the topic today, which is going to be trying to analyze the performance of the antenna in a wider environment. So, the main goal is to try to assess and investigate the communication link between a fixed base station, for instance, that is set in an urban environment, and a vehicle-mounted receiver, such as the one my colleague Jehun has just showed. And the idea is to try to assess this link over a trajectory in that scenario. So automotive scenarios in general in Winprop, we have two different types. The first type is when we are trying to assess perform a test in a relatively large area. And the second one is when the radio channel analysis is of interest in smaller areas. Starting with the large area scenarios, this is what we would call an urban scenario in Winprop terms. And in this case, the buildings and the terrain data can be included in our simulations. This can be performed over multiple kilometers or over an area with multiple kilometers square of size. The typical propagation models that we use for this type of simulations is either the dominant path model or the urban IRT model, which is a ray tracing model that uses pre-processing for acceleration of computations. In this case, the receiver antenna effect is also added to the simulation in a post-processing phase. And this is how we can include also all the properties of the receiver. Usually, the geometry of the car itself is not included since we assume that the effect of the platform on which the antenna is placed is already accounted for in the antenna diagram of the receiver. And the second type of analysis is where we're interested in communication in the channel or the communication between the car and infrastructure or other cars, but in smaller areas, such as intersections between different streets and in a given scenario. This is for us, we use the term indoor scenario in Winprop because in these cases, the database that is used includes all a high level of details. It also includes the car geometries, and that can be set to be time variant in the sense that it could move in our environment. And in these cases, we use the standard ray tracing model to perform our prediction simulations. Usually in these cases, we are not interested in big area coverage, but we are mainly interested in some points in the simulation space, such as it can be related to the radar of the car and so on. So in these cases, we have fewer points that are computed. The transmitter itself can be set as a fixed infrastructure antenna, or it can also be a moving antenna on one of the vehicles or any other moving geometry in the database. And of course, we can define some time variance accordingly in our tool Wallman, where we can set all the start and end time and the time steps with which these geometry objects are moving. So today we will be focusing on the first case where we are performing virtual drive tests in larger areas. So for that, we need to actually to have our inputs ready to be used, such as the antenna pattern of the receiver and the transmitter, but also we need the multipath environment. And for this, usually we need an urban database. There are multiple ways you can prepare that. Either you have a CAD geometry of the urban area, or you can also use some online open source websites such as OpenStreetMaps, where you can export your database. Here, as we see on the left, you choose the area and you convert it in Winprop into a Winprop usable database. So we have a video that explains all these details and the workflow. You can find it on our Altair How To YouTube channel, and you will be able to see all the steps of preparing your urban database for Winprop. So actually, the overview of the steps we will be checking today in this demo is to see in ProMan how we could set up such a virtual drive test. So we will be interested in communication data rates as well as received power signals. So we will be defining a network planning project. We will be setting up the base station and configure the antenna parameters, as well as we will see together how to set the trajectory for our receiver, which is basically simulating a moving vehicle. And also how we can run the simulations and define all the parameters related to the moving mobile station. And the main capabilities that we will cover in a bit is actually to see how in the tool we can perform these different steps, including, for instance, how we can add the receiver antenna pattern. We're going to use the antenna patterns that were generated in the first part of our demo today. So I will be using the antenna pattern that my colleague Jaehoon has just showed you. You can use either the one that where you place the antenna on top of the vehicle, or the one inside, and then you can compare the performance of that receiver antenna given its place inside or on the vehicle. So let's move on to the demo. We'll start from scratch by creating a network planning project in Winprop, and we will be using a LTE air interface and checking the urban database that we have used. In this case, I'm using a part of Frankfurt downtown that I have already prepared and converted using the OpenStreetMap database online. So now that we have our database set, we will start by creating our base station that is made of that is going to be a 3-sector antenna. The next step is to set the details of the antenna. So I will be changing the height of the antenna so that it is on top of a building. And I will also use an antenna pattern that I already have simulated for a base station. And I'm also setting up here the received power parameters of that station, the carrier at which I want the antenna to use. And I'm repeating the same steps for all 3 antennas in the base station. And so it is important to assign correctly the antenna patterns as well as the carriers, as I've mentioned. So once we have set that, we can visualize in the background the horizontal and vertical patterns of these sector antennas. And then I will switch to the 3D view so that I can see all my antennas in the setup. And here I see clearly that I forgot to raise 2 of my antennas. They're inside the building. So I will quickly correct that from this Site tab. So indeed, 2 of them stayed at 15 meters, which is inside the building, and now all 3 should be located correctly on top of the building. In the 3D view, you can see the exact representation of the antenna patterns. Next, we will be setting the trajectory of our mobile station, so our car in the streets. For that, we use the trajectory tool. We simply geometrically on our 2D view draw a given trajectory, and then we can access the detailed coordinates of each point of the trajectory from the project parameters from the simulation tab. So here we see our trajectory has appeared. It has 9 points. You can modify the heights, the XY coordinates, as well as the velocity of your vehicle. And you can double check that all is as you want. Now we will check out the requested network outputs we want. So we can add some throughput outputs, signal to noise interference ratio. So here you choose which output you would like the tool to compute as well as save. and also the propagation results. So we have the received power by default. We will add the propagation path so that we can visualize them later. And it is in this tab where we will be able to add all the parameters related to our mobile station. And here is where we activate the mobile station parameters, and we can add different types of antennas. In this case, I'm going to set a single antenna, and I'm going to use the pattern that we have just generated with where the antenna is on top of the car. So I'm going to use that gain pattern. So in my simulations here in Winprop. In the Sites tab, we have already checked that, and now I have all set. The computation, I will be using the dominant path model. It is quite a quick model, but you can also use the IRT model. Now I'm just saving my project and I am running the simulations before we check the outputs together. It's relatively quick simulations because the dominant path model is a numerically quick and optimized model. But yeah, as I mentioned, another option is the IRT model. So checking the results of what we have done, we have the propagation results, of course, so the received power that includes the MS station parameters and with and without. So the power results without the MS station are actually used by modeling an omnidirectional ideal receiver, but also the network results that include all the post-processed results based on the air interface and the cell assignment we have in our air interface. So you can also see the received power that is accounting for all the parameters in the air interface. You can see all the carriers and which carrier is dominant over which part of your trajectory. You can check out the throughput and the data rate of your communication link between your mobile station and your vehicle. So all this is accessible in the network results. Now, another thing, you could view the rays actually over the propagation path. And for that, here you can choose which pixel you would like to check the rays. And we can view in the 3D view, we can activate an animation. So here, since we have chosen the dominant path, each pixel point of the receiver has one dominant path, but you can see if it is a direct line of sight path or if it is a reflected path, and so on. So this is the general overview of the workflow of how you can assess the performance of any antenna you have designed in FECO when it is placed in a real environment with all the multipath effects and potential interferences due to the environment. So this is it about this part related to the virtual drive tests.